Hi. Um, as usual, let's check the audio. It's working fine. So if you for confirmation. So welcome Juan, welcome Daniel, welcome everybody. Okay, thanks for the confirmation. So let's go straight to the. Okay, we're back to Unreal now. Think maybe the other way better. This like, to pay attention to. Oh, it's kind of here. So see the folder structure stuff, but seeing the content is okay. So we're back to Unreal, and just like the previous series, this is gonna be multi multi stream thing for real. So we start today. I don't know if it's gonna be like 3 or 4. How many are necessary for us to finish this? So the idea is to start something almost from scratch and then move on to have something playable that we can play test at the last day. So I'll start by just turning this on and so hi William again. So I'll start by testing this here so you guys can get an idea of what we're gonna do next few weeks. So this is Unreal with Quantum running, and this is already there's a lot of stuff already working. So the idea is that we're gonna make this kind of like electric remote control car going through an empty street kind of thing in Egypt. So whatever fits the assets I had at my disposal. So that's basically the idea. We're gonna be tweaking a lot this areas, this physics stuff, and playing around to make this work like we want. So let me add a few comments here. So hopefully this is gonna work fine on the stream. I'm not so sure because Unreal is very demanding. I might experiment by lowering the visual quality to make sure it doesn't get very choppy. Hey Diogo, long time no see, so welcome. Um, so yeah, I might need to because when playtesting this while streaming with OBS using the video card to encode the video, it might get a bit choppy. I'm not super sure about it, so I'll give it a try to see. But if necessary, I can lower the quality settings and then we're good. So I wanted to add a few comments here. So of course this is Unreal, and you guys see that we have something playing. So I'm actually playing online here. So this is running already local physics prediction and everything. So let me stop this here. Um, so this is already running playtesting online here, and I wanted to add a few comments. So although we're using Unreal for the rendering, the whole simulation is running actually Quantum. So the physics engine is our custom predict rollback physics engine with fixed point numbers, and all of the pre-built components we have for Quantum Unreal already in place here, all integrated into the Unreal editor. So I wanted to clarify that. So we're not using chaos physics, we're not using Unreal's netcode at all. So we're gonna play test this. So let me demonstrate this running into. I think I will already read quality settings just to make sure it doesn't get too crazy low. So I'll run two those here, so we can see this in action already online. Just make sure get into the same room and but with different nicknames. So we actually together here. So we have one car here. I'm going to control the car on the left and the right, and you guys can see on the other screen that it's running here. So let me crash into that. So yeah, it's running in sync just fine. So this is actually connecting to the our cloud in Europe, and that's also what we're going to play test with later on. So the idea is that we're going to build a small racing game. So this is the track layout I prepared here, and so essentially I got this asset pack, and I organized this by making these. So what I did is I added our own static mesh collider to these things. So the data about these triangles, it's all being baked in our physics engine for the static part of the environment. We have a few other interesting things. So I added these. So I created these blueprints for an actor that actually uses our physics components, but not only a collider, but in this case, a transform and also a physics body. So we can crash into these boxes, and they are actually dynamic physics bodies. So this is all using our own physics, and I'm gonna try to show how you get Unreal when you set up a scene to run Quantum and explain the topics. But of course, it works better if you guys ask a few questions, especially those of you who are experiencing Unreal itself and understand how to what is a game, what is a game mode, what is an actor, what is an actor component, how you implement specific actor classes and add components to them. So in C++, and then use them as blueprints. So we're going to be doing a lot of this here. And of course, if you guys ask questions, I understand better what you guys are, what kind of questions you have, what are the stuff I should talk about. So let me check what is being said here. Okay, so great question, Jaken or Jaken. So it also works offline, so without internet connection. So it is really good for that, because let me give a few interesting, let me add a few comments on that topic. So you know that Quantum has been available on C# as an ECS game engine since 6-7 years already. It's been battle proof, tested a lot. And this is a brand new implementation, totally done in native C++, built to native libraries and everything for all the platforms. Still cross-platform deterministic, but so we do offer it running offline and online. So essentially, you can have multiplayer game, and it behaves like as if it was a local game, but it's running online. But you have multiple player inputs coming, and some of these inputs are from local players, essentially. But you can use the same code and run the game locally and without internet connection, even for multiple local players. This works both online and offline. So you can add, so if you have a split screen kind of game, you can, let's say, have a couch version of it that it's just local people playing together for fun, no internet connection required. But you can also run online, even with, let's say, 2 local players from this machine playing against one player on a Nintendo Switch. That kind of cross-play with asymmetric number of players is also available. So both cases are supported. I have to be clear. I have to be clear that the current state of the early access version, funny enough, has only the online version, which is the most complex. It's on our very, let's say, high priority task list to make sure you have also the local mode to test. One interesting thing, so what kind of stuff this adds to you besides super snappy local like physics? Those of you who use our C# version of Quantum know that we have full replays and kill cam replays out of the box. So essentially you can while the main game is still running, you can load a new instance of the game with the starting from one snapshot, and you can replay, let's say, less 10 seconds in slow motion, something like that, or even record a full replay. And we plan to add this type of support to Unreal as well, because fundamentally the engine has a way to do that. For Unreal, because we're embracing the actor model, it's going to be slightly more challenging, let's say, because loading a replay, you're going to reuse the same existing actors you have. Some are going to be spawned, despawned when you do that. But because we do support dynamic spawn, despawn, this is possible to do. And if you're careful when you keep a very nice split between gameplay logic and view logic into your actors and blueprints, and you split that, really organize that well, you get that kind of stuff like full replays and kill cam replays out of the box. So it's an interesting aspect, and the cool thing is that that also works on a local game. Even an offline game can have that type of stuff. So okay, so thanks for the question. Let's move on here a little bit. So just if we're starting from scratch, so how does a quantum game work? So essentially you load Unreal and you load a map and you're gonna play on it. So how do you make that run under quantum? So we have so we designed the whole thing to at least the controls for it as an Unreal game subsystem. So essentially, assuming, for example, an online game, so essentially what you can do is if you have a new scene, for example, what you can do is you can create you just add you connect and join an online room with an API from the subsystem, or you can directly do a slightly different type of matchmaking. But let's say you're just using the subsystem, you have a couple of methods, a couple of functions you can call into the subsystem to connect to our cloud and get you into a room. And then there is one specific call you do to start the quantum game. So when you start a quantum game, this local subsystems is communicating with our cloud to send a few configuration things and requesting, hey, can I join whatever quantum game is running into this room? If it's not yet running into this room, let's start it. So then this set of protocol messages back and forth make the server start kicking, and then the server coordinates the tick timing, and what starts to happen is the local simulation is now starting to run. And if you don't have any specific quantum actor, it just has an empty simulation that it is ticking, but it doesn't simulate anything unless you manually spawn stuff. But normally what you would do is you would have a couple or a handful of actors that are already, let's say, quantum actors into this map that is loaded when you start quantum. And then the quantum subsystem is going to scan the map, the existing actors there, for this specific quantum interface, and it's going to add these to the quantum simulation as a starting point. So I'm assuming, for example, people starting at the same time. So what we have here in this particular case, I'm going to show the actors that are actually quantum actors. So we have all these crates. So I showed all the elements that have these mesh colliders, but these are not really quantum actors. They have this component fixed mesh collider just to be able to bake the static collision stuff into what we call a quantum asset. It's a data asset in Unreal that is going to be loaded as part of the initial simulation, but these are not necessarily actors that are running the simulation itself. But these crates are. So they are specific. They are instances of one specific quantum an actor class that implements the quantum interface. We're going to show that. But I do have a couple of more that are interesting because they are the two I'm actually using to kick things off. So I use this menu spawner. This is a normal actor just to spawn the widget for the menu, and the widget for the menu is the one that's actually doing the calls to the subsystem to start Quantum. But this one here, spawner, is one that I'm going to now show the C++ code for. It is a quantum actor. So it is an Unreal actor that implements the quantum object interface. So quantum is going to scan the map, and this is one of the objects it's going to find. So it's going to call certain virtual functions, certain callbacks into this particular actor. And I'm using a few things from this particular actor. So when you start Quantum Unreal or in C# Quantum 3, we have a new protocol in that you always start as a spectator. So when you first play, you do not have control of a player. So we're not polling the local game for player input at all. So whenever you join or start a game, you are just spectating the simulation in time, doing prediction and everything in runtime, but it is a spectating instance. So adding a local player is a dynamic operation. So you can add a local player or remove a local player. But normally when you're playing an online game, you have at least one local player. So essentially what you do is you start the quantum simulation, and right after you request to the server, oh, and by the way, I want to control one player. So there is one function on this subsystem called add player. And this is one of the things I'm doing from this particular actor here. So this particular actor, after Quantum is started, there is a callback that says, hey, Quantum started, the simulation is running, it's all set up. And all this simulation, so for example, these boxes, they're already dynamic rigid boxes that are being simulated by physics. But what I do is I react from that with a blueprint implementable callback, and I use that loop back to say, oh, by the way, I want to control a player. I want to add one local player. And when I do that, it's when I spawn the car. So I'll show first the blueprint here for this. So this is the blueprint of this class. So we see that it extends this class called deterministic actor, which is one empty actor that we offer that implements the quantum interface. You can just extend this one or just implement the interface. It either work. You don't have necessarily to inherit from this actor called deterministic actor. In this case, I'm actually I'm implementing a component. So the player spawner is actually a component. They both have the same API. A quantum actor or a quantum component that's part of a quantum actor. But what I wanted to show is the. Oh, I thought it was. I thought it was here on the event graph of this, but it's not. It's fully on C++. So let's take a look at the C++ code. We can close the editor and open again when. So quantum player spawner has these functions here. So this is called from the menu. We're using this to start the quantum online game, but the ones that matter are these here. So on init, once the quantum simulation starts, on init's going to be called, and this is the one we're using to call another function in the same actor, the same component here, to add the local player. So we're basically, as soon as Quantum starts, we're saying, hey, by the way, we want to play as a player, add one local player to this machine. I could call this twice to actually, for example, control 2 players, or 3 times. How many is supported this particular configuration you're doing, which is up to 128 players in total for a single game. But of course, it's demanding to do such a big game, but technically, this is not a hard limit. The hard limit tops at 128 for Quantum. So then, after we call add player, that actually sends, let's say, a player loadout object. We're not going to talk about the loadout configuration stuff and webhooks to validate that with backend, which are all available already from day one. We're not going to dive today into those details. We're just going through the loop, the basic loop here. But that submits this request to the server saying, hey, I want to control one player. The server is going to decide what is going to be the player index that you have control of. There is an important about this, because if you disconnect and you connect again, you can try to get control of the same player you had before. So there is a secret key that you send to the server. You would only give that player to another client if there is not anymore a new slot for a new client. So it tries to save the pre-used player slots to a reconnecting player as a reconnecting client as much as possible. But when that's confirmed by the server is going to send, as part of this input stream, data about, oh, by the way, there is a new player that's now a live player as part of the full input set for every tick. And it comes with the loadout that this player chose, this serialized object about the chosen loadout, which we're not going to talk about today, but in another stream. But it ends up calling this on player added. And this is a pretty interesting callback, because if you have, let's say, 10 clients executing the game right now, and there is an 11th player joining or whatever, this is going to be called on every single client exactly on the same tick. So spawning, let's say, the vehicle, the physics vehicle, the blueprint instance of the vehicle that is controlled by one player is going to happen on every client, because it's a deterministic simulation, and it happens exactly on the same tick. So this is all happening on the implementation of this class. So we call from the menu. So if I press go again into the engine and we press connect and then start, that's gonna start Quantum by calling this function. I don't have to dive too much into this because this is starting from the subsystem. What really does the meat is eventually this is going to get called saying, hey, the simulation started. And from this one, I'm calling, oh, this one, because I want to add a local player once the simulation is started. This sends another message to the server to do that. And when the server accepts that, this is going to be called. So these two were called only local on my machine. When I join, of course, only needs call on every machine as well, but that's, and then eventually when the server confirms my player was added, this is called, and that's where I'm spawning the vehicle. So let's take a look at the actual C++ code here. Does that. So this is just the interface, just the declarations of the function. So let's see the definition. So player spawn. So let's start with onInit. So when onInit happens, so this here is basically serializing the player loadout Unreal struct as a JSON to send to potential webhook validation. We're not going to dive too much into this right now. We also got data. I'm sorry, this is receiving the main game mode loadouts, which is another object that sent. But essentially, as I said, what it's doing is I'm calling add player because I want to control one local player. This is going to say I will have control of my first player because I'm calling this once. Then this sends something to the server. The implementation is essentially I'm preparing the loadout struct, player data, as JSON. And essentially I'm calling on my subsystem. As I said, we have a subsystem, so I'm getting the instance of the subsystem here, and I'm calling add local player with data attached to it, which is the loadout data. And I'm saying, oh, I want to add my local player 0, which is my first local player, and with this data. And that's going to send a message to the server. So whenever the server accepts that, if it does accept that, you will call on player added on all machines, and this is where the spawning is happening. So on player added confirms the data that we received and what is the player index out of the 128 possible that this is going to be controlled. Which player index out of the possible 128 this guy is controlled. So I'm getting this loadout thing, but let's ignore that for now. I'm just logging some stuff that I sent from that. What matters is this. So I didn't show, but I do have a property here for the subclass of deterministic actor. So what is the quantum instance, quantum class that I want to instantiate to be controlled by this player? So it's a subclass of deterministic actor in this case as well. And the implementation essentially spawns that using the define player class here. So later we're going to modify this to allow you to select from 2 or 3 cars, and we're going to spawn the blueprint out of the car that you selected if possible, protecting against errors and everything. So then I because this is a kind of like a generic spawner that I can use for characters and for cars, I use this as a test spawner for everything. But in this case, I'm checking, oh, is this possibly a subclass of quantum vehicle, which is a pre-built actor that we have for vehicle physics. It's given in source code, so we can fully modify. We're gonna tweak a lot this guy over the next few weeks, but I'm checking here. Is this a car? If it's a car, then I'm going to initialize some stuff. So first thing I initialize is, oh, by the way, the player who's going to control this car is this player index here. So I'm going to be grabbing inputs from this player for this particular instance of the car. So if you have 4 players, we're going to have 4 cars spawned, each one controlled by a different player. And this is just a test thing. It's not really relevant to the gameplay. I was just showing that you can store pointers into the game state. And what matters is that I spawn the car in one of the possible spawn points, which is an array of spawn points, is an array of this struct called spawn point. This struct basically has a position and an Euler angles rotation for where your car will start from. So I'm preparing this for up to 6 players in reality, so I have 6 spawn points created on on the version that is on the map. And yeah, the spawn points come both with position and row. That's essentially what I'm doing here. I spawn the car like that. So that's all for the spawner. That's what spawns the car. For those who have not seen the previous video, has never seen the preliminary documentation we have about Quantum Unreal. We need to talk a little bit about rollbackable game state, which is where you're gonna do your game logic to stay deterministic. So what Quantum does is for every class, either an actor class or a component class that you set to implement the Quantum object interface, Quantum code generates using the Unreal header tool a struct, and it adds a pointer to this struct and calls it QState from Quantum state. And it's going to contain the properties you decided to be rollbackable. So this allows, as we'll see soon, this allows you to add, so you can have normal Unreal properties to your actors and actor components, but for properties that you want to use for game state, properties that need to be rollbackable, you're going to define them using a specific set of Unreal property macros that we offered, which behave exactly like uProperty macro. So we'll talk about that extensively during the next few weeks. So in particular here, a vehicle has some data about a car as rollbackable data, like the wheel colliders positions, the wheel speeds, and current suspension compression values, and a lot of stuff that is part of the simulation is part of that. But it also has a normal transform, a normal collider, and a normal rigid body, which are pre-built components, actor components that Quantum has. So we're going to explore a bit this pre-built vehicle class that you can just use if you want, but it's nice to understand how it works because you can fully modify it. So let's just run this again so we see again this in action. I'm going to show some of the menu blueprints so we get an idea of how this sequence works. So this is a bit like how I do stuff in Unreal. So I code the actual logic in C++, and I use Blueprint to glue things together, sometimes trigger the calling of some functions here and there. And because Blueprint is very easy to prototype with, but it gets to a mess pretty fast in my experience. So you see and we take a look at this menu thing. So we have this menu spawner thing that essentially has it has a blueprint to spawn a menu widget. That's the only thing it does, and so it spawns this special widget called menu UI. Let's take a look at that widget. That is this guy here. So this is so it's a set of buttons to do stuff and some text boxes that you can press type stuff. But it becomes a mess as soon as you look at the the blueprint. But I'm gonna cut it short. So essentially, it calls stuff on the runner subsystem. Essentially, it calls connect to connect to our cloud. It may call disconnect if you ask it to. There is stuff to send a command, which is a special type of input in Quantum. It's not the regular input. The regular input happens with a polling approach. So this is so we use it to unflip the car. If it flips, we use this idea of a command. But it has another function called so start Quantum. It calls on that actor that's already on the menu. It's not yet Quantum. Quantum is not yet running, but we grab the instance of that particular actor spawner, and then we get the class called Quantum Player Spawner, which is the component that we show the code for. Then we call start Quantum in it. And when that is called, it will call in the subsystem to start Quantum and everything. And the boilerplate stuff here is essentially to disable and enable the buttons as it is. It's a mess, and you guys can criticize and judge my blueprint prowess, which is close to nothing. But it just starts stuff. I'm not this part about the stats is not in use anymore from here. I'm using a different way to show the stats. But essentially, let's do it again from a single go to get the best performance possible. So from here, so here it is. I'm just flash with it. Connect. So this connected, asking the subsystem to do, and this is going to call in this guy here function called start quantum, which is going to forward to the subsystem to actually join a room and start quantum, and that's going to trigger the whole loop. So we're going to get the, if you look at the output log here, you'll see some things happening. So okay, so in sequence, essentially we Quantum registered all the actor components, all the actors it found in the scene that are Quantum objects. So it found the spawner itself, it found all those crates, and it registered all of them to have all the deterministic callbacks called to them. And then the spawner one got that on init called into it, and it asked to add a player, and that's what triggered. So that logged this here saying, hey, I received this runtime config thing. So this is from the onInit function that we saw. And then it requests add player to the subsystem, which sends a request to the server asking to control a player. And that when that returns, we get the on player added callback that we saw. And that is essentially logging new player connected. And this is the data that we decoded that we received, which is the same that was sent. And then it triggers spawning this Stinger class, which is this vehicle here. And it also registered the collider for it and a few things, which is something that happens. So the full loop is complete here. Oh, my camera is in front of that. So thanks, Daniel. Let me switch here, and you guys can see what I said, right? So the initial registration of all the existing ones in the map, then the onInit being called was this log here, and then after we sent the add player, when we got the callback of on player added, we spawn this vehicle for this particular player. If I run two screens, we'll see this happening twice in the log, both. So this we'll see happening twice because each one of the two clients is going to register all the existing scene objects or map objects as part of the quantum simulation. And this here received runtime config, which is the only, it is also happening twice because it's the two clients. But this one here is going to be interesting. I want to do it like that to show to you guys how it goes. Unfortunately, we're not logging the player in. Let's just try to get it running here. This clear that, and we're gonna call start here. So we got the register twice, but I'll stop here just to show the log because I'm interested in the log only. So we get the logs for registering. So it searches for existing quantum vectors, it registers all these in one of the clients, then it does the same on the other client because this happens immediately after I press the start button. And then we got the two onInit callbacks from the two clients. So both of them received the runtime config object from as part of onInit, and on that spawner actor that has an implementation of onInit. But this is the funny one that I wanted to show. So the new player connected. We have player 0 and player 1. So they both got connected on the same tick 64. And they got their car spawned, the two players. But then we see the same stuff again. So why is that? It's because we're spawning the two cars on each one of the clients. So two players, we need to spawn two cars on my client, and the other client also needs the two cars. The car that's controlled by the local player and the car that's controlled by the remote player. So that's why we see log 4 times. It's two cars, two clients. Okay. Hope you guys understood all this. Please again ask questions if you have any. That helps a lot us understand everything. And thanks again, Daniel, for pointing out that I was at the log and it was visible. Let me see what should go next. Here, I think the spawner doesn't have any state. I don't want to go for that now. So let's take a look at this pre-built vehicle physics thing that we have. So as I said, this is not really so this is not Unreal's car physics. So this is our own car physics. So I wrote the car physics for this based on the previous experience me, Daniel, and other devs have on building the C# version of this. In the end, it's just vehicle physics, just done in C++ in this case. So I wrote the actual car physics on top of our physics engine building blocks. I can comment on all that. So if anybody here is into vehicle physics, we can go pretty deep into slip models. But I want to try something here. I'm not sure this is going to work 100% fine, but I will try to spawn the other car model I have here. Fuck. This guy here. Let's see if it actually still works. I'm not sure if it's 100% screen. I'm not sure this is gonna work. I crash. It actually did. Or I don't know how well this is gonna behave with the settings I have here, but yeah, working. Okay. Yeah, but this should be bigger because it's kind of a more plain car. Okay, it does work. So let's go back to our Stinger. And shall work again. Really with now. I've been tweaking for the past 2 days. Yes, sir. So yeah, so this has all been tweaked and developed by us. And let's dive a bit here. So let me check the question here. Um, these are not scripts, right? So these are C++ classes that it depends on what you're talking about. So documentation is being written. There is some preliminary documentation, but the vehicle physics actor, we're going to show a lot of it, comes in source code. So you can look at the source code and understand what it's doing. It's not ultra complex. It's a pretty straightforward arcade physics model with a slip computed per wheel, a suspension compression computed per wheel, and all that. It has Ackermann's variable radius steering and all of the shebang you expect. Let's say it's kind of like a GTA like style physics, but documentation is mostly code. You look at the codes, you know car physics, you understand. So this is not really drag and drop stuff. Although I'm showing the drag and drop part, which is I didn't modify this vehicle package to start what we're doing today. I just used the one that I had already developed just for testing. I didn't modify it. I just used it as it was, and I just made this car. So I had this other one. I had this particular car. So I had this car preset as is the stuff that we test on our main repo. It's been there for a while, and but to start this series I said, okay, I need to have a different car. So what I did here over the past 2 days is I got these 3D models from another sample we have on Unity, and I loaded this in Unreal, I got the shaders and everything set properly for Unreal. But I used my own actor class for vehicle, and basically I tweaked it, distances and the configs and everything. So it's all these data assets we're going to show now. So I tweaked it to be this particular vehicle. I haven't even finished yet the arm kind of rotation, and it's a point that I wanted to discuss, for example. So if you guys have never done car physics before, it's incredibly complex to do little things that you take for granted. I'll give an example. So when we set up these cars, we know when whoever creates car physics modules, let's call them that. So in this actor is a specific, it's a vehicle physics actor that works with Photon Quantum C++ for Unreal specifically. It's designed for just that. But I defined the class with a lot of pre-built stuff that simplifies you to start some stuff. And one of the things I add is this hierarchy of actor scene components that allow you to just drag and drop graphics for part of the moving things of a car. Because to get the car behaving visually like a simulation like you guys saw, it means that you have to have a car model made out of totally separate parts. So you have the body, which is kind of fixed, but then each wheel has a different separate 3D model with the pivot point being exactly at the center so it can spin around itself. I do love C++, yes. My first language was C. I learned to program with C. So C# and other stuff was like a byproduct later on. So I'm comfortable with C and C++. Yes. It's, I mean, game development is C++. Even if you do C#, you to do best kind of stuff, you go closer to C++. Yeah, you can do gameplay stuff without it, but people who build the engines, and the engines are 50% of the games, they're all built in C++ most. Anyway, enough ranting. So So if you take this is the wheel. So you see here where the pivot point is. So the pivot point of the wheel is this particular point, yeah, where the cursor is. And so normally for a car suspension and wheel setup, you need a hierarchy with 3 different points for you to know what to do. So, and this is just for the visuals, right? So the actual setup of the car defines an anchor point where the suspension is gonna, assuming you're doing with ray casts or with shape casts, which are 2 approaches for doing this. So you need the anchor points for where the axles start from, and the logic code is gonna find where the contact points are with sometimes dual ray cast per wheel or a shape cast with a cylinder or something like that. And then you find the contact points, and that defines how far the wheel is from the car to touch that, and that defines the amount of suspension course and how much force is going to apply based on the damping, on spring damper algorithm, and sway bar computation. We're going to dive into that later. But once that is computed as part of the simulation, which defines the forces on the car and everything, we need to then update the visuals to match what the simulation did. So the visuals are a consequence of what the simulation did. And this is what I'm talking about here. So this here is just visual setup. And for each wheel, you need at least 3 elements in the hierarchy to get the whole thing right. So you need what I call a suspension point, which is just to, so the only thing we do on the suspension point is this movement here, up and down, up and down, up and down, based on the suspension compression. Then you need another entry point on the same, at the same point under the suspension thing. And the only thing that this one does is rotates, it's to do this, which is essentially to turn the wheel left and right. So this is what you do with the second level. This is what I do with the second level. And then the third level will be a wheel thing that is essentially the one that's used to do the wheel spin part of it. So when you drag and drop, when you create a new blueprint class out of this class of mine here. So let's do that just to show an example. So if I want to create a new blueprint class, and the class is going to be quantum vehicle. Here it is. Select that, and I say my vehicle. If I try to set up that, doesn't have any visuals. Doesn't have anything. I could have created some boxes. I will probably create some boxes to simplify for people who are starting fresh, but essentially it just has that structure, and it has a link to a vehicle config, which defines a lot of parameters of the car. We're going to dive into those soon. But the anchor points for the visuals are all here, and they're updated based on the they're updated based on the config stuff you link here. And but you start kind of like this, and then you have to add all that. But what I wanted to get to, which I'm gonna get to now, I don't need this also delete it. What I wanted to get to is that is just for the, let's say the brake calipers that get on the brake, because those go up and down, and they also move with the steering, but they do not rotate. So we need to get a visual for the brake calipers. So let me show on this car what that is. So it's this. So this is the wheel hub brake caliper. So this does not rotate with the wheel spin, but it does rotate with the steering of the car. The back wheels don't, but they still have the same structure, because some cars can do opposite back wheel steering. This physics does support that, but this one does not spin like that. And then we have the mesh for the wheel that includes the disc brake. These rotate, spin. and they're under the other, so they also do that. And both go up and down with because the main suspension one goes up and down. Cool, but this is just for the wheels. So if you see these suspension arms that I'm adding here, to get these suspension arms to actually rotate correctly with the car, I can parameterize the code for that, and I'm going to do that. But setting that up and calibrating the angles and everything based on the distances they have from the anchor point of them, which is in this car, is particularly easy because it's at the center point. So we can compute the distances basically easily. But the angles that these move with, they are proportional to the amount of compression on the suspension of the wheel you have. And but different car models may have a different number of these arms, and they may have different sizes, and then the angles are not the same. You have to calibrate with the sizes or the angle multipliers and something like that. So it is quite challenging, and this all requires your artists to do all this with the pivot points at the right places. So if you click on this, so this is perfectly done with the pivot point at which it should rotate. The same for this one. So this one gets the pivot point right at the center because that's where it should rotate. Which is the time for me to say something. So this particular 3D model is perfectly created for physics-based physics. So this was created by the guys from Red Cat Pick in Portugal. So big thanks to them and Brian in particular, who's been a partner in stuff. So this particular 3D model is used on another sample we have on the Unity version with Quantum Unity, and this 3D model has all the right stuff in place that allows you to set up it to behave correctly. So you have to have all that. So if you're doing custom car, in whatever engine you are working, you need these visual setups to be done manually. And sometimes you do need to modify the source code to get this right. Because sometimes your 3D model is not exactly on the same anchor, so you need to calibrate slightly different, or you need to at least tweak the value. So you need to understand a bit this to do it. This is not going to be the topic of the whole stream, of course. So I'll do the setup for the suspension arms off camera, and I can show the final code for that, but that's not the point to do that code during the stream. I'm just talking about the topic because it is an interesting topic. There is one let's say, meta conclusion that I wanted to get to. So did you guys notice that I haven't talked about networking? I haven't talked about replicating data here and there, or what do you need to get this networked? And this is the point. Don't need anything, because quantum being deterministic and predict rollback deterministic, running, let's say, at 60 hertz, which is the case here, you don't need to think about the game as an online game. You just think about the game as a game that has multiple players, that you have these callbacks that get called, and that's it. You don't think about replication. You think about a local game. If anything, what you try to do is it's good for you to split gameplay from view, from rendering, because you have the gameplay code that rolls back, resimulates to get everything snappy, and then after that you update the visuals of whatever you need based on that. So that's what I do, for example, for these wheel visuals. It's like the whole simulation runs, and the end result of the simulation, before we render the updates, we call a callback called update view that updates the positions of all these wheels, and it's going to update the suspension arms and all that. And then that it goes to the Unreal renderer. So, but yeah, so you don't think about netcode much when doing stuff with Quantum. You just think about gameplay, and that's what we're going to talk a lot about, is like, how do we tweak the physics of the card, or the one that we would like to play together. Or a lot of the topics here are going to be, so in a nutshell, let me try to write down here what the topics are going to be about. So it's vehicle physics weeks. So we're going to play around. We're going to look at the code and see the actual car physics code here, the whole API for it. What is the game state of the car physics? If that is something interesting for you guys, we're going to talk a lot about that. So Nicholas's question about are these scripts tweakable? Yeah, here's a full source code for the car physics. So this is the .h file for the vehicle physics. Here's the whole API for the car physics. Even the private stuff that gets called to update all the stuff. So raycast stuff to get the suspension compression, updates the force based on the compression that was found, updates the wheel slips, the wheel spins, the drivetrain, which is how much torque the engine is making, and that. So and the actual source code is all here, so it's not stupidly big. It's comprehensive, well organized. At least I like to think. I understand it up and down any way I need. So it's given in source code. So we're gonna talk about a bit about that, about tweaking car physics, modifying source code if necessary for that. That's one topic. But we're gonna also talk about racetrack and racetrack. I mean, not the surface of the racetrack, but mostly racetrack checkpoint, which is what is the best way to know where a car is in terms of its position on the track. So my idea is always to make a series of trigger areas that are checkpoints, that once the car passes there, you pass through that checkpoint, and we always know. And what we do is we do a linked list, a circular linked list of the checkpoints. And so the car, once he passes one checkpoint, it knows what is the next one, and it stores that the next one he should pass through is that one. So what do we do with these checkpoints? So there's a few things we can do based on knowing which. So knowing where a car vehicle is in relation to the track is done by tracking which was the last checkpoint you passed through. And I'm not talking about like long checkpoints that say, oh, you passed through this checkpoint, now in 1 minute you're going to pass another checkpoint, like in a rally game. I'm talking really about very close to each other. So a track like this, I don't know, we're going to have 20 checkpoints or more. So the idea is to always track where the vehicle is, because there are a few things we can do with this. So one thing we can do with this is we know how far a vehicle is into the race. Laps. So we know how many laps you've passed. Every time you pass, let's say, through the main checkpoint, you count one lap, and laps plus how far into the distance in lap. So distance in lap is essentially the so you can compute the distance in lap by what is the last checkpoint you passed, and you know the accumulated distance from the previous checkpoints up to that point, plus the distance you are in the direction of the next checkpoint. So you do a dot product of where you are compared to the last checkpoint in the direction of the next checkpoint, and that gives you how far you are towards the next checkpoint. And because we know how far each vehicle is into the race, we can use that to compute positions. So we know positions. We can know who is first, who is second, and so on, because it's essentially who is further into the race is first, and so on and so forth. And then we can also know if you're going the wrong way or not. So we know that the direction you should be more or less going towards from the previous checkpoint to the next checkpoint, which is the one you should be going towards, and we know the direction the car is facing. We can use dot products here to tell if you're going in the more or less in the 180 degrees direction of the next checkpoint. So it's the kind of stuff, and because we know the wrong way, we can also perhaps use a cursor, like a 3D cursor, pointing you the direction you should go towards with some form of interpolation. So you can do a lot of stuff just by using checkpoints. You can also use this to build bots, AI, racing game AI to compete against. If you have only two players, we can fill in with the four bots and run that. So I plan to actually implement bots at the end of this. So we'll finish the we'll do the racetrack checkpoint stuff, implement all that during the stream, and at a later point we're gonna just dedicate one stream just for bots based on that. So that's one thing. We're gonna do just enough of UI, just enough. Essentially, stuff like gauges, RPM, speed, the velocity, speed, kind of stuff. Uh, we'll do positions, perhaps a cursor, that kind of thing. Uh, countdown, lap times, which is something. So lap times. So lap times we also do with checkpoints. So you start counting time, and then after when you cross the checkpoints, set and you store. Okay, this was my lap time for the previous lap, and so you can do all that. It's all based on checkpoints in the end. That's how you do. We're gonna use triggers for that. So that's in a nutshell what we're gonna do here. And if you see, there is not really topics. There are not really topics about netcode, because when you use quantum, netcode is kind of behind the scenes. It's deterministic, and it does also support late joins. So it's not you can start the game and somebody else can late join. Of course, in a racing game, that's kind of tricky, but technically the SDK supports serializes the game state from all bodies and sends. It's all done automatically behind the scenes for you. So okay, so these are the topics I plan to explore during the stream. But one thing, first thing first. So what I plan to do today is just show a bit about the car physics stuff. So we do have here the blueprint for the car. It does have basic physics component, pre-built quantum components like transform, collider, and body. The collider is an interesting one because you see I have a very basic compound collider. I could have made a more complex compound collider here, but I decided to go for this. From the perspective of the physics collisions, this is the car. The wheels are actually extra raycasts for the suspension stuff, but these side colliders here, so the wheels in reality they go a little bit up when you press the car. So they're gonna be around inside this, and this is good for when you have side collisions. So doing an open wheel car design is more challenging than doing a base one. So but this setup normally works pretty simply. It's much could also try to move up and down these compound colliders. I think that's overkill. It's not really necessary. You do the raycast for that. It's better. Um, and this box here as part of the physics body is something that we offer, which is a way for you to set up the inertia tensor. So those of you unfamiliar with car physics, so one of the secrets to getting stable car physics is playing around with the physics body inertia tensor. And this is a very nice way of setting up an inertia tensor. So this is stuff implemented by Daniel, who's here on the stream. So it allows you to set up the inertia tensor, which is how resistant a body is from rotating or being moved, or depending on each axis. So rotating the car as a yaw like this, which is what you do when you turn, is proportional to the area of these two axes we see here. It's this big rectangle area, so it takes a while. Rotating the car, pitching the car up and down like this proportional to this section area here. And rolling the car left or right at the turns is it's proportional. The resistance is proportional to this area that we see here, this frontal area. So it's pretty intuitive to set up inertia tensors using this. We call it parametric inertia. There are other ways you can set up the vectors directly, or you can let quantum compute the inertia tensor based on the mass and colliders of the car. But it's much better to control based on this. And if some people ask, do you play around the center of mass for the car? No, we do play around, but we try to position it to where it looks like where it should be visually based on the car model and where the engine of the car is. So because then the car behaves really well, especially when in the air. So you don't play around with you don't need to play around much with center of mass to make the car stable. It's more like I do other tricks to get that to still allow you to roll the car and yeah, and totally roll it over. But you don't play around the center of mass because that behaves better. So this is just the basic stuff, the basic physics stuff. So what is specific to the car physics? So so our base car physics model all starts with a data asset called vehicle config. So it can get pretty complex, but I'll split it into parts. So first you have the configuration about the axis, and there is a specific separate data asset for the wheel, which tells what is the mass of the wheel, radius, what are the parameters of the wheel itself. But the suspension of a specific axle you set here. So you set what is the suspension height, 50 centimeters, travel, and what is the parameters in terms of spring and damper, all in metric units here. And this is the offset of the axle. So basically from the center of mass of the center of the transform of the car. So this is the rear axle. So it moves on the x-axis, which is the forward axis in real. Move back. So this guy is small. So this is in meter. So it's like 0.70 centimeters down. It's like a big remote controlled car. So this is what we're building here. And the axle starts, at least the raycast down starts from this position here, and it uses it's this distance here plus the radius of the wheel. So that's how the raycast is done. And in z-axis, oh sorry, mistake, total mistake. So y-axis in Unreal is the lateral axis, so it's the right axle. So it is 60 centimeters to the side, 70 centimeters to the back, 60 to the side, and vertical is z, so it's neutral. It's from the center of the car down, plus the radius of the wheel, z. Anti-roll factor, I'm not going to dive too much into car physics. If you guys have a question, if you guys know what this do and you want to ask, please do. You define if it's a traction axle or not. So the rear one is not the steering, but it is traction. The front one has very similar setup. It's slightly a bit more to the front, and but same sideways distance. It's both traction and steering. So this car is four-wheel drive, but it steers with the front one. Then you define the steering angle of the front wheels, the maximum steering angle, and the Ackermann offset, which is the stuff to make the different wheels have different turn radius when doing that. That's important for stable physics. There is some. So when you go very fast on a car, you don't turn the whole wheel like that. The faster you go, you normally are more careful with your steering, because otherwise you spin the car really easily and you get understeer. So I have a quick tweak that I always add to my car physics, which is I start to smoothly clamp the maximum steering angle and I start that at around 20 meters per second, and from there on it clamps, does the full clamp, so the smoothing happening between 20 and 30, and then it gets, if it gets at 30, it's already at maximum steering control, and basically clamps the angle maximum at 10 degrees. So you normally can turn slowly at up to 30 degrees, but when you go fast, it clamps to 10 degrees smoothly in these two speeds. Then tires have a specific config for them. We're gonna see them soon. Drivetrain have one for engine, one for gearbox. A few extra tweaks. So where to apply the side anchor. So this is a tweak that I get to get very arcade physics and the car not roll very easily, because we normally in games we use a lot more grip than in reality. So the car would just instantly roll over. So we do not apply the force exactly where the contact happens. We apply it actually closer to the anchor points of the suspension with this offset. So it's the anchor point down about 5 centimeters, and that allows the car to roll, but it's not low enough to make the car roll over very easily. This is a tweak. You can do the opposite, which is you can turn off this and apply actually at the contact points and use an offset on the other direction, a positive offset, but that's much more difficult to control. If you put 0 here, you would basically be real physics like, but then you would have to make the car a lot slower, use less gravity, less grip, and it doesn't really feel good to play like that. So I like to do it. I'll not get into all of them, but I like this one a bit. So this is a bit like, I think it's missing one. This should be more like the way I did it. Um, so a curve, a friction curve of a tire normally looks a bit like this. So as you go, I'll leave it. It's a bit like when you, this is based on how much slip, how much the wheel is spinning and slipping against the contact point. So you start with a bit of grip, but as you add more slip, you increase the grip factor, and it gets an apex at some point which is not with a lot of slip, and then it drastically goes down and stabilizes at normally at around 0.8 maximum grip. Once you're spinning the wheel, I mean the wheel's slipping fast enough in any direction, the maximum grip you get is about 0.8 of the maximum. And this is pretty much how, if you want to do an arcade tire, this is how the curve should look like a bit. And the other parameter is essentially defined for you. So asymptotic slip essentially defines where is the maximum grip point, which is this one here. So it basically says the maximum grip is going to be about at 1 meter per second slip, like the wheel, that's maximum grip we're getting. And the extreme force is how intense it is, because this is a normalized curve. So the maximum here is 1, if you guys see on the left here. It's actually 3 newtons that each wheel maximum can apply. So this is how we define it here. But the cool stuff is that playing around with these values let you make the car drift a lot more, or be very grippy and controllable. And it, I can spend hours just pressing play and tweaking these values until I'm exhausted. So I can spend hours and days just doing this. It's something I have fun with. I'm not gonna do too much here because I haven't set up that I like, but of course when we play test, you guys can give feedback and we can modify and do one more play test with different set of values. But engine torque or power curve has a similar setup with a curve, but it is done it has a slightly different kind of curve. Resembles a bit this. Uh, and max torque, max RPM. So the right side is the maximum RPM. You don't get the maximum torque and power at the maximum RPM. It's actually below that. So you start to lose power too much. But one thing I wanted to comment about these curves is what are these numbers? Because this is the Unreal editor for a float curve. So what we do is we reuse the Unreal editor as a float curve, but what we do is we sample this and create a lookup table using our fixed point number. Because when you modify it and you save the asset, it actually uses this resolution here. You can change. Let's say I want to use 64 entries samples on the lookup table. Normally 32 is more than enough, but it actually saves the lookup table of fixed point numbers and it interpolates in runtime using the fixed point numbers because they are deterministic. So we don't use the float stuff in runtime, just bake with it. So, but it's cool because we reuse the existing Unreal editor for a curve. We do the same thing and that's very handy for you to define these data assets. So if you're curious about this, so what is this? How do you create these data assets? How do you use this in Quantum? You can create any Unreal class, and these are just regular data assets. So it is part of the vehicle. Let's take a look. The actual state. I want to see I think there is a separate. Yeah, setting. Yeah. So let's get one that we took a look at. So the tire config that has the curve for the tire and the asymptotic slip. So that is just a regular Unreal data asset class. Using regular Unreal U properties, I added the comments here so we can look at what they mean. So that was the tire. So to rest the mouse over, it adds meters per second value will divide the past velocity to normalize it to the desired range. Affects slip speed at which apex friction is evaluated. Dang. So tells it all here, and but it's just a regular Unreal data asset class. And we have this particular struct type called f fixed point numbers, runtime curve, which is what ends up as this editor. So it's very convenient. Curve here is what it should grow from near 0 to 1, then come down to around 0.8 time 0, 1 because it's always normalized. Here's the extremum force, so I give formula for the tire slip stuff here. So all these settings, so they're normal Unreal data assets, and to create a new one, I want to have a new SMISC. Oh, miscellaneous here. Data asset, and then you define tire config. So this is the quantum. Grab from here, and then you create a new one. Done. Not gonna do it. Then you create one from scratch, and then the car config. You link all of them here. Engine, gearbox config stuff, and the wheel, which defines the radius, and a few other things. Find all this from this central data asset, and your blueprint for the vehicle actor has one link for the vehicle config. Has a few other tweaks, like I found this spacer tweak necessary. I'm not gonna talk about this. We can also play the game seeing some physics gizmos, so it's sometimes useful to debug what's going on side of things. So yeah, you see the wheel contacts and the vectors that are done. So if you run this on offline and pause, you can are. So it's quite handy to sometimes, especially during developments. See how much force is being applied to it. I like to use these things. Actually, it's not necessary. A few other, so let me comment a bit on this blueprint here. So when the car is started, there's something specific to Quantum here that's worth mentioning. So let's take a look at the car API, vehicle API. So it will be spawned by Quantum. And one thing that we called from the spawner was, we call this thing here called init UI. So notice two things. I set who's the player who's controlling this car, and I call init UI. Whenever I spawn a car, I'm calling this for the first time. So this is specific. This is important. This here is not about gameplay. It is about being able to initialize the visuals of the local player car, not the others. I'm interested in the local one. So then what it does when this is called, so this is a blueprint implementable event. So there is no implementation of this here in C++. This is done in Blueprint. My first actual use. So here's the implementation of this event. So what happens is it gets the player index, which is the player who's controlling this car. This is a read-only Blueprint function that grabs what was that player index that I said. And then I get the quantum subsystem, and the quantum subsystem has a function called isLocalPlayer. So basically, it lets me know, okay, I just got this new car spawned, but is this the car that's controlled by the local player or one of the other cars from guys? So this grabbing the player index of who is controlling this car and checking if this is a local player lets me know that. And what I do is, if it is the local player, I set the camera to be the one following the car. I set the viewport to be the view target to be that, and I have a spring arm camera attached to the car, and that's how it goes. I do that. I also link the telemetry widget that shows the car parameters and slips and stuff for debugging purposes. You can totally disable this and get rid of that. But this is useful to debug. There's another thing I do here which is quite interesting. That's quantum specific, which is I also grab for the local player only, but every tick, every update, I set something called prediction sphere, and I get essentially where the car of the local player is, because I check if it's a local player. So if it's the local player car, I get the position where it is, and I set one thing called prediction sphere. So that essentially tells Quantum, hey, the local game client is only interested in stuff inside this area here. You don't need because Quantum is deterministic, it needs to simulate with confirmed inputs everything, but you don't need to simulate stuff that's not being seen. And we have a few different ways to set this, but one is like just set an area of interest for you, which does not need to be the full frustum. It can be just a smaller area around the player. So this is very important to control performance of prediction. So some people ask when they start to check about quantum, yeah, but how can you do a lot of physics objects because you're rolling back and predicting like a fighting game all the time? And if you have 30 players, how can you? So two questions here. So first, do you predict rollback everything all the time? And here we see that the answer is no. We only predict stuff that you are interested in. Although, you can predict 1,000 physics bodies fine on a PC. But of course, if you were predicting only 10, 20, it's going to be cheaper and you can render more stuff instead. So that's first answer. Answer number two that people, for questions people ask, isn't it crazy to have, let's say, 10 players running determinism? What if one of these players do not send input in time? Is everybody going to wait for the input for this guy forever and roll back pretty long stuff? The answer is again, no, because that's why we have a server in the middle. So the server only accepts inputs for one specific tick up to a limit. We call this hard tolerance. So it's a setting you configure in Quantum, and essentially, if you have 10 players and one player does not send input in time, his input is going to be ignored if it doesn't reach the server by that limit. and the server sends overhauls and sends confirmed input on behalf of the player. So both the player and everybody may roll back with the confirmed inputs. I mean, Quantum always rolls back, right? But the point is, but it's pretty clever in that it tries to repeat the previous input of the player based on a configuration we have, which is the same that the local prediction does. So when there is one input that was replaced by the server, two inputs that were replaced by the server, you are not going to notice because your local prediction, if it's another player, you're not going to notice because the local prediction of your game already used that value for that player and the server confirmed with that, although it was done by the server, but it used the same one. It does that up to a limit. But even the player who's doing stuff, normally you don't notice if it's just one or two inputs that are got missed on from your machine. Because in a game like this, you're pressing accelerator and left and turning. You're gonna stick to the same controls for a few frames. You switch controls, I don't know, 2-3 times per second max. So there is a very, very, very good chance that the server replacement is going to do the same stuff that you are already doing. So not only you, not only others, but you also don't notice when there was a bit of network loss and just a couple of inputs got missed. So this is in a nutshell what the server does besides controlling time. It allows for this. It's this crazy thing that you can do 128, 64 player games with determinism is because there is a server in the controlling that kind of thing. And that's why games like Stumble Guys, who is built in Quantum, can actually do 32 players on mobile and play great. Because it plays great because it uses the same backend tech. Although the simulation engine is our C# ECS version of Quantum running on Unity as the renderer. This is a totally brand new one, but it does use the same backend. So the server side stuff is the same that you get from it's the battle proven backend stuff we have with a native Photon server run some server log. So this is a bit about the car here. So I would like to give a few minutes to see if you guys have any questions. Because as I said, I think I work much better if I get some nice questions like I had before. That helps me also feel a bit how you guys are understanding everything. It a few see higher. It's very slippery, something like that. Aside, just again. So yeah, so now it's sliding like crazy. So it's basically a drift car. Oh, I gotta was I was actually running under network loss and extra latency to test put it on. So this is like a drift car now. Basically, I'm sliding completely out of control all the time because I have almost no grip on the tire. Same for brake. But it is finding the sweet spot that allows you to roll drift is kind of cool thing. See, it ended up. Yeah, it's kind of challenging, but you can do all-wheel drifting. It's kind of um. Let me go put it back. I'll put it in at 2.5 instead of 1.5. Yeah, it's still drifty, but much more controllable. I bet guys would find it very hard to control when it's like this. So I'll leave it at 3, 5 for the play tests and everything. Time. Then I'll take a look at Daniel's question. Yeah, this is much more creepier. It has its own challenges when it's that doesn't drift, but gets very sticky, especially at low speed. I have to say it again. I'm running here at a pretty lame visual setting, so it does not get too choppy, but it looks really cool if you are not streaming at the same time and you can actually use quality of what you can do on your local machine, especially on a build. It looks so much better. It's going to be a bit choppier, the rendering here, but it's nice to see the shadows and everything. Always impresses me that you, even if you do a very basic level like this and how good it looks, you know, it's because of the lighting mode. Let me take a look at the question. Yeah, Daniel, thanks for that. I actually noticed that by watching the stream again, and I should have this before. Um, I think, not sure I can control this without jeopardizing the stream at the moment. Maybe let me see. So it might. Scene. This is a black scene, so you guys don't see me, but I do have my microphone. So what is the noise suppression? Suppression level. Noise gates. Perhaps I'm gonna disable actually both. Yeah, and disabled noise suppression and noise gates. Let me go back here to. Okay. I'll stop talking and then go back to talking. Going back to talking. Going back to talking. I think it's gonna be better now, so I shall leave it like this or tweak it a bit better later. I might do a test stream with you guys with that. But thanks for the tip. I need to get a different set of settings for this. Yeah, so this is what I actually planned, and I can still cover a few questions, but let's put a bit back here. So essentially, if I check here on my plan for the stream itself. Um, some basics of quantum unreal, basics of vehicle physics, the map track layout, so setting up collision geometry, and chatting about the next feature. So this is basically what I wanted to have covered. I've done most of it, but I still have time for a few questions. Um, and but we got most of it covered. So one thing I didn't show much is how do you define then, how do you differentiate between game state that you want to be rollbackable and game state you do not want to be rollbackable? Although I covered this on the previous stream, let's take a look at that in the vehicle itself. So this is quite a complex one. We're gonna do a few other actor classes or components that we'll use that have rollbackable state later that will be simpler and to understand, but this, because this is pre-built and it does have a pretty complex set of stuff. So essentially we have multiple Unreal structs, F structs, with the macros that are specific for quantum, and but then everything is basically regular Unreal properties. We just make sure to use only deterministic types. So instead of using float numbers, we use a fixed. Instead of using a vector in Unreal, you use a fixed vector 3, which is the 3D vector. We have the 2D vector. We have a quaternion for rotations and all that. So we have all these F structs that would be, let's say, deterministic data structs with types that can be assumed deterministic here. And then a command, and then on the main actor class, the vehicle, which also has the quantum macro, we do have some regular U properties, and these regular U properties are just, let's say, read-only stuff or stuff that is used only for visual components. So remember that I have the links for the visual for the hub points of the hierarchy of the visuals of the suspension and wheels. So these are actually default components I add to this actor. But here is the actual meat. So this is one way to define rollbackable state. You use this macro called QReplicate, and you use the type fxl state in this case here, and the name is going to be rear axle. So that Q state struct that gets generated will have a field called rear axle, which is this type, axle state. So these are all rollbackable properties that will be part of Q state. There are three other ways to define this. So the QReplicate just allows you to define an entry into the rollbackable struct, but it does not allow you to, let's say, from the blueprint, create an initialization value. So it's fully procedural data here. There is another one which is, we call it Q property, which is the same as a U property, but you would put what you would define into the rollbackable struct and add an extra entry for you to initialize values from the blueprint. So it's good for designers. So these two can be combined to get the rollbackable state partially zeroed out like these here, and parts initialized from the blueprint by designers. And the other way is to define one main struct that you control everything and make the whole rollbackable struct that struct. So that's also possible. So let me take a look at the question here. I think it's a coincidence. So very good question, Tech 131. But let me give you one example. So let me get something here. So Quantum is predict rollback, so although it does use a bit of CPU, it's not different than in any physics-intensive game. In many cases, even with rollbacks, the physics of Quantum is not more expensive than something done with PhysX or Chaos on a single-player game. And especially because of the prediction culling stuff I showed you, you can make your game basically CPU-wise behave like a single-player game because you're only moving forward. So say you can run the simulation at 40 Hertz, 40 ticks per second, 50 maybe. You do not need to go full 60, for example. So physics engines normally run at about 50. So say you run Quantum at 50 or something. And because you have a restricted area for prediction, the whole simulation is actually running at only 50 Hertz. It's not rolling back everything. The only things you are rolling back are the stuff very close to the camera, so it doesn't really use a lot of CPU for the rollback and resimulation. It's mostly a forward-only game, just like a single-player game, with the complexity of simulating everything. So it's CPU intensive in the way that you're not gonna build a massive survivor, huge world game with Quantum. You're gonna build a smaller type of game that you want very, very tight physics and a lot of interactions. I'm gonna talk about the rendering in a minute and give a counter example of what you said, but I'm also explaining the whole thing. So normally what you want out of Quantum is this very, very intense interaction, and that means it's a certain type of game. But performance is really very fast. So let me show you something here. I'm gonna run this with Quantum stats, and we'll see how fast this is simulating all these rigid bodies and this complex vehicle physics and everything. And I could add a lot of cars. And you see this number here where the cursor is? It's difficult to read, but I'm gonna read for you. This says time in microseconds. So this is, it's less than 1, sometimes 1, rarely 2 milliseconds for the whole simulation, including rollback. And I am not using prediction culling here because I'm actually setting a very big prediction area. I was testing this. So this is essentially rolling back and resimulating everything. It's not resetting, it's not really simulating just around the car. It's simulating almost the whole, it's basically the whole thing, because all the moving stuff are inside the prediction area at the moment. And it's stable here at about 6, yeah, it depends on how many predictions I do, but it's between 0.6 and 2 milliseconds total. And this is a debug build inside the editor, not really running. This is also running single thread. We're not yet running multi-threaded like we do on the regular Quantum C Sharp. So this is just using one thread for everything. Our physics engine can fully run in parallel, for example. But so this is pretty fast already. So what you do is that you don't go crazy on the size of the game. You do what you need to do, and then performance of the CPU is really, really good. But what you get is that because Quantum actually performs so well, we do have a lot of mobile games. And mobile games, you normally go for low rendering anyway. Successful mobile games like from Supercell, they never go crazy on graphics. You do crazy on graphics if you're doing a shooter. You almost never do a crazy graphics on a mobile game because you want to run on very, very low-end phones. But I'll get to the counterexample. Let me get a link, and I'll take a look at the next question right after. So let me just grab YouTube here. And I can do a reaction video. So I'll get this. So this game, I'll not run the, maybe I can run the audio. Unfortunately, the audio is not going. Why isn't it going? Anyway, we don't need the audio, but let me show gameplay. This is just cutscenes, and yeah, this is gameplay. I know because I played this game. Played the test builds. So they've been doing this game with Quantum for the past. So this is gameplay. This is actual gameplay. Oh, damn it. This is actual gameplay. This is actual gameplay. And this is a Quantum game. This is also gameplay. This combat is all gameplay. So it's typical Moon Studios flair. Nice graphics. PC, desktop, desktop and consoles. You should expect this. And this is made in Quantum, and the simulation time on this is really, really under control. They're pros. They work very closely to us, and they do great stuff. So I'm really, really curious to play the final version of this game when it comes out. So yeah, it depends on what you do. So you can do a pretty interesting game visually with the CPU budget you get. I think it's more that there is a lot of mobile games done in Quantum. So Mark Fielding, no. Quantum does not do syncing state. Quantum does not replicate anything. Quantum is deterministic. The only thing that goes is input. Absolutely nothing to do with that. The only time at which Quantum transfers game state is if someone late joins, either from the server, if you have server simulation running, which is an option in Quantum C Sharp, or normally one of the existing clients is going to serialize one snapshot of the rollbackable game state and send that through the room one time, and then it's deterministic and it's only input from there. So Quantum does not do state sync at all. Has nothing to do with that. So no, it's really, so it was a very, very good question from Tech 131, because it's an interesting point to understand how much should you be able to spend in CPU, how much you should dedicate for rendering. And I think the rule of thumb should be the same as a local game. So you can you should consider that in my rule of thumb is like if you spend less than 4 milliseconds in gameplay simulation, it's perfectly fine to get 12 milliseconds for rendering, for preparing stuff for rendering, not necessarily rendering. And there is even one thing that we can, as quantum developers, we can explore here. So again, now that we're kind of starting fresh with Unreal, which is, so bear with me here. So on Unity, we run Quantum triggered from the Unity main thread. And although Quantum then splits into its own task system that uses multiple threads per platform and so on. So we normally in mobile you can use 2, on PC you can use 4. You can assume you have 4 nice threads to work with. For the simulation, it does a lot of stuff in parallel, like physics engine, and even user systems can run in parallel. Quantum does that pretty well. But it's triggered by the main thread. And then at the end of all that, it starts the rendering. So it uses multi-threading just to be able to do more, but it's still triggered from the main thread. And you may ask, can't you just run the quantum simulation on a separate set of threads and let the rendering thread work in parallel? So although technically we could do that, and we had in Quantum 1 a way of doing that, there is a problem with loading assets. So we added dynamic asset loading for Quantum Unity on version 2, and that has to be loaded from the main thread. So the whole thing has to lock the main thread to run the simulation and then stop, to be convenient for the developers. But the guys, for example, from Moon Studios, they always discuss with us, and they are actually running from a separate thread. So they run the quantum simulation from a separate thread because they preload the assets they need. They know what they're doing really, really well. And they actually run the rendering in parallel to the simulation. And this is something we can also do here. And I'm planning to add that option turnkey because I expect Unreal developers to understand those concepts really well. And it shall be a no-brainer to run Quantum in the background while the rendering is running. So essentially, you have the full 60 milliseconds for simulation, assuming you split, you have CPUs for that on a decent platform. But that comes with a grain of salt, which is something that Unreal also has, which is Unreal in general has. When you have that, when you run the simulation on a separate thread, you need to use some buffering and interpolate between two simulated frames to align that correctly with, so you have to copy that data and align that on the visual actors, and by using directly the actor model, that creates a little bit of a tricky aspect of, should you access data directly, should you do the stuff separately. So it's a little bit tricky to have we would have to store, essentially we would have to store different pointers for the quantum state. We would have the simulation state that is accessed by the simulation threads, and there will be a view state, which is a previous copy, or two of these, double buffering that, so you can interpolate between those without touching the one that's being modified on the fly. So it becomes a bit trickier, but we can revisit that topic and essentially split the whole thing. Well, Tech 131, I would try the opposite. So Fall Guys does not run on mobile, and it does not run on mobile for two things. It's not the rendering, it's that the way they did physics and netcode does not work on mobile. Stumble Guys runs on, so the fact that Stumble Guys' Steam is paired down with the mobile version was a design choice. Actually, the Stumble Guys' Steam version runs with a lot to spare. It does not use almost any CPU on the PC. They could have done a much nicer rendering on the PC version. It's their choice. And if you look at the current version done by Scopely, the graphics are getting much better than it was originally with Kitka. It's about development resources and how much you can do, and the new team and publisher, they can do a lot. And then it boils down to design and resources for that also. So even though they are improving on the graphics, it's much better now, it's still a lot of effort to have a totally different renderer, for example, on the PC version compared to the mobile version. And especially on the mobile version, they have a very big audience that has mid-range and sometimes low-end phones. So it's actually it's kind of the opposite. Quantum runs really well even on low-end devices, and that's why Stumble Guys exists and has this many players, is because it runs and runs really well. Whereas other people tried that kind of gameplay, they failed. And so in the end, the graphics are a design choice to be able to access that audience. And on PC, they are improving a lot. It's a new choice they can do. It still needs some resources to do it. It's I'm not judging, right? So I'm just guessing. They could do however they want, but it's not a limitation on that side. It was more like a design choice. And you also said something interesting. See, it's targeting mobile. Most players on those games are playing from mobile phones. So there are a lot more players on mobile phones than Steam. So they still like the Steam version because people who play tournaments and are competitive on the game, they always play the Steam version. But Scopely is adding a lot nicer graphics to it, looks like. Probably it's still more mobile focused. So yeah, I think they're doing a great job actually. Um, So Albion uses Photon Server, although it's so they use Albion is an MMO. It's a totally different type of game and a totally different type of target, right? So we're not aiming at that with Quantum, not even in a certain way with Fusion, but I'll talk a bit about this soon, but Fusion I mean. But Albion is uses Photon Server with their own code running on the Photon Server, and it uses replication directly with Photon real time as a transport layer. So it does use our products, it's built on top of it. They use the reliability and all that from Photon Server, but it's not one of these high-end products we have. They use just real time transport layer. It's been built a long time ago. The guys are great. They know what they're doing. They squeeze a lot out of the Photon Server. They actually put a lot of players into a single server with the logic of the MMO running there. It's great stuff. There are some presentations from them, but it's not related to what we're talking about here today. Um, no, yeah, it's okay, but it's okay. I can mention that because that brings a hook about. So this is that we've been talking about here is quantum is a deterministic engine that comes with physics and a lot of other stuff. And for Unity, we decided to go on a totally split programming model using our own sparse-set ECS. A lot of people like that, but on Unreal, we decided to do the opposite. We decided to integrate a lot with the actor model. So we were not forcing you to decouple stuff, although it still makes sense to have very clearly decoupled rollbackable game state from visual state and auxiliary read-only data assets and things. But we're not making that very super explicit. You have to do it, but it's how to organize things is your choice. It's all done on top of Vector and stuff from Unreal APIs, and we did that because we want it to feel as familiar as possible for existing Unreal developers. So that's why. And but I wanted to mention Fusion as well. So we do have this replication tag for actually synchronizing the game states, both with client server model and with a client authority model, which is called Fusion. And we had this flagship sample that is a battle royale with 200 players running at 60 ticks per second, both on the client and on the server, the simulation. So if you compare, Fortnite runs 30 ticks per second and it's 100 players. So we could get with it, we did this with tick accurate animations, with sub-tick accurate lag compensation for shooting and all that. It's basically a tech demo of what you can do, but this was all Unity. But what I wanted to say here, because this is all about Unreal, is that we're also working on a new replication tech. So we have this almost ready to be shared with Circle subscribers. It's so Daniel, who's here in the chat, is the lead on this now, and he's I'm just I started all this with the team, but I'm now using. I'm eating our own dog food, creating this sample live, and demonstrating stuff. But they are responsible for developing the whole thing now. So this is Quantum. This is almost ready for you to use. Um, but we're also baking under the scene, behind the scenes, a new replication tech. So you think about Fusion for Unreal. Um, but it's going to be different. It's not Fusion. It's something specific to Unreal, native C++ stuff with some different design choices. But the idea is to up the threshold for Unreal netcode replication as well. So we're doing the deterministic one with this, which is Unreal does not have. They have their own cool netcode for replication, but they do not have anything that to cover what Quantum can do. So we're building this as a product, but we're also building something for replication, which is to be better than even what they have. Let's see how that goes out. The judge is going to be customers in the end. But I just wanted to mention that, not talk anything technical too much about it now, but we'll have time to talk about that when the time comes. So, yeah, I still have about 3-5 minutes. So if you guys have the last questions, feel free to ask. And I don't have yet the schedule for when it's going to be the next stream, but maybe even still this week. I'll check. It depends on how much I can do behind the scenes. I want to probably organize some clean stuff for the checkpoints and see what I can do, because then but I'll not program everything. I'll get the data, but I'll let the logic code to be done live for this next part, so you guys will understand a bit better how to do the stuff. But and also it's going to be a lot less data, so it shall be easier to understand. Let me take a look at the question here. So at a high level, what approach would some take to fill races with bots? So Mark, thanks for the two questions. So because it's kind of a bit late into the stream, I'm gonna give you some resources for reading, because we do have a preliminary, very early draft document about what you can do with Quantum Unreal. Let me grab that document. Quantum Unreal. I think that's it. Oh, 9. Intro. Quantum Unreal. I think that's the name. It's a just give me a second. I have to find the document link here. It's a hidden doc. Oh, it's a hidden doc, but I can share. It's oh. Okay, quick start guide on Rio. That's it. So let me paste it here and show. Then I'll share the link with you guys. So this is a hidden document. And it has a lot of stuff about what is a basic actor component in Unreal, how you do the minimum version of in this case it's a actor component, implementing the interface. I'm using the not the inheritance but the interface implementation version, and how you define predict rollback game state. So it explains here Q replicate, Q property, and the other one, and it shows one at a time. So here it shows how you do Q replicate and what that ends up generating. It generates this struct here that would be, and the Q state will be co-generated using this generated struct. So doing this in the actor component. It's going to create this struct, which is going to be also declared like this. And then what is the other way of doing it? It's using the Q property, which is essentially a normal Unreal U property, but starting with a Q, but with the same options. And what it does, you define as a Q property, and you have to suffix it with prototype, and it will allow you to edit from the blueprint. So you will show up here on the blueprint for you to fill in data on a blueprint instance, but it will be added to the Q state without the prototype suffix. So it does the same as Q replicate, plus lets you have the level editing side of things with the Unreal stuff. And the other way is defining the full struct yourself, and setting it as your quantum state root. So the whole struct is going to be the one you define. So that's less likely you're probably going to use the other two combined. And there's some other explanations about the callbacks and some stuff you get. We're going to be updating this doc, and Quantum Unreal is going to be have its own product page soon, and we'll add a lot more docs. But let me link this here into the live stream chat, because anybody can access this and take a look at what we already have documented. Okay, so this is it for this doc, and then the last question you had about bots, that's very, very, very interesting, because I actually plan to implement bots as part of the stream. So yeah, here it is. I said this at the beginning. So the very last stream is going to be about implementing a basic racing AI bot. And the idea is that we're going to have a few players in the countdown, and the ones who do not show up, we've closed the room and fill up with bots. And I'm going to implement a basic racing AI bot, but you get an idea of how you can do this and what you can do to get bots. And the interesting aspect of bots in Quantum is bots run as part of the simulation. So you do not use one of the clients to send the input on behalf of a player doing the bot on Unreal, because you don't want the bots to depend on one particular client, because if that guy disconnects, the bots are gone. So the right strategy to do bots in Quantum is to run them as part of the simulation. And you can do the bot decisions only on verified frames, so that it's the same as a local game doing bots. It's a single player game doing bots. It only runs on the forward verified ticks. And what you do on the prediction ticks, you take the decision from the verified one and you accelerate, keeps turning, you just predict them doing what they last decided for. And when it's rollback corrects the decision, the differences are very tiny, because the car does not react so fast as 3-4 ticks. It takes a while to actually change. So let me see what else we have. Tech 131. Well, when you use Unreal, unless you're doing blueprint only, you are always using pointers. So everything is a pointer in Unreal C++. I mean, even this, the actor, if you get your begin tick this, it's a pointer to your own actor class. So yeah, if you're doing gameplay code in C++, you do use pointers. We do use ref stuff sometimes, but sometimes I even do a ref to a pointer, which is a double pointer kind of stuff. But yeah, it's pretty much mandatory to use pointers when you use C++. Ref can be used sometimes, but we're talking about low-level structs stored in a separate rollbackable heap. It has to be pointers. When using blueprints, no, you will show some stuff that can be linked via blueprints, but to write gameplay code, it's C++, and then you have to use pointers. Even in Quantum C#, you do use a lot of pointers. So yeah, that's pretty much necessary, yeah. So this, yeah, this stream is available out of sync right after. Thanks, Daniel, of course. It's right after. I mean, as soon as I stop here, if you click on the link, it's the beginning of the stream. It's probably already processed and all. Um, Um, uh, Daniel, that's a long shot, right? Porting the bot SDK to C++. But we can, I'm pretty sure we're going to provide some add-ons with examples of how to do, more like text samples of how to do, just like we're doing. So this vehicle physics here is given in source code and it's going to be improved. And it's kind of an add-on that you use or not. We have a base character controller already using capsules and it will be improved and given in source code as part of the SDK. And perhaps we're going to have some building blocks for bots. Yeah. Maybe I will do that. I don't know. Let's see. I mean, it depends a lot on the demand and how many people are going to start using this. Maybe I will even venture into doing some bot add-ons in the future. Let's see. Oh, you're talking about the Unity version. Technically, you do not need to use pointers all the time. So you could get a copy of the component, work on it, and set it back. But that's a lot more work. But the reason to use pointers is it's structs, C# structs. It's better to use pointers. It's faster. You get faster code. Yeah, Daniel already talked about it. Whenever you get a copy of a struct and you have to set it back, it's more error prone and it uses more resources because you're getting a copy and then you pass it back. Just grabbing the pointer is faster and less error prone. You make less mistakes. So yeah, it's not really for structs. Getting a pointer or a ref to the struct has the same meaning and you get the same result out of it. Okay, so I have somebody tagging me here on our internal Slack. Let me just check that that is not related to this here. So I can add a few comments if that's the case. No, it's not. It's something internal. Okay, cool. Daniel, thanks again for the comments. That helps a lot. And yeah, if you guys don't have any last second questions, so let me check the one from Mark. Mark, so it's we never give concrete ETAs, right? So we can never commit to specific ETAs, company policy, right? But we expect to be within the next month or two, hopefully. And yeah, it's not really far. If let's see how many ask about this, because it's almost ready and we will be very close to the early adopters. So we have two samples already built on top of this. So we had two teams who already used this and developed game samples. It worked great. One team from Austria, one team from Finland doing this. We have these two samples available. We have this that I'm building now. And we'll be very close to the early adopters in support in Circle, of course. But we need a few more weeks to polish a couple of points. Daniel is the lead on that. Maybe he wants to add a couple of comments, but that's about it. So thanks, Gabriel. Okay, thanks for the question, and thanks for listening as well. It was great. Um, yeah, Daniel already gave the answer. Cool. Daniel, thanks a lot for joining as well and answering some stuff here again. Yeah, last thing, as I said, I might announce another one for Friday perhaps, but it's more guaranteed that I'm going to do early next week, the next one. And the next one is going to be about checkpoints, doing lap counting, time counting, lap times, and all that. And getting the racing stuff actually done. Okay, so thanks again for joining and see you guys next time. to stop it from here first. Oh no, it's better if I do